You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Professor Avi Loeb. Avi Loeb is the Frank B. Bird Junior Professor of Science at Harvard University, Chair of Harvard's Department of Astronomy, Founding Director of Harvard's Black Hole Initiative, and Director of the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics. He also chairs the Advisory Committee for the Breakthrough Starshot Initiative, serves as the Science Theory Director for all initiatives of the Breakthrough Prize Foundation, as well as Chair of the Board on Physics and Astronomy of the National Academies. He is the author of 4 books and over 700 scientific papers. He is an elected Fellow of the American Academy of Arts and Sciences, the American Physical Society, and the International Academy of Astronautics. In 2012, Time selected Loeb as one of the 25 most influential people in space.
Avi Loeb, welcome back to the program for what must be the 15th time. We're celebrating 15 or so interviews, but there is a lot to discuss today. And where I want to start is your recent paper on black holes, which, as I recall, you were working on black holes for a large part of your career with Stephen Hawking. And now we're looking at primordial black holes and how they can accrete or not, more importantly, not accrete. So say we have a primordial black hole left over from the early universe sitting inside of a star. What prevents it from accreting material?
Well, it's sort of interesting because we don't know what most of the matter in the universe is. We call it dark matter, and we knew about it for 90 years. And we tried to search for elementary particles that might constitute dark matter. We haven't found them in laboratory experiments, in the search for particles coming from space. So we don't know what dark matter is. And one possibility is that these are mini black holes, tiny black holes formed in the early universe when in special regions, rare regions in the early universe that was dominated by radiation, there was a high enough density of radiation for the region to collapse upon itself and make a black hole. And this should be a rare occasion just because we know that matter constituted just about 1 part in a billion of the number of photons. So we know that ordinary matter is much rarer than the radiation energy density in the early universe, and the same holds for dark matter. And so we just imagine those rare regions making primordial black holes. In that case, those black holes, if they have the right masses, could constitute dark matter. And astronomers have been searching for primordial black holes of different masses. We don't know what the mass of those black holes was. And we're able to rule out a wide range of masses, because if you had the primordial black holes with a mass comparable to that of stars, they would magnify the light from background stars if they happen to be along the line of sight to background stars. And by monitoring millions of background stars, we were able to set very tight constraints on the existence of dark matter in the form of primordial black holes with masses that are above the mass of the moon of Earth. But there is still a range of masses that is allowed. Very small mini black holes would evaporate through the process that Stephen Hawking pointed out about 50 years ago. And they would just be short-lived with an age, with a lifespan that is less than the age of the universe. And we don't expect them to make dark matter. However, black holes between the mass of an asteroid with a size of roughly a kilometer up to an asteroid with a mass corresponding to a size of up to 100 kilometers, that is still an allowed range of primordial black hole masses that could make dark matter. And if you check what the size of the event horizon of these allowed black holes, you find that it's between the size of an atomic nucleus and the size of an atom. These are tiny, So even though they have the mass of an asteroid, a very massive asteroid, the asteroid, the Chicxulub impactor that killed the non-avian dinosaurs 66 million years ago, was in this mass range. It was a huge rock the size of Manhattan Island that collided with Earth and changed the climate, raised a lot of dust, created havoc, and basically 3/4 of all life forms went extinct at that time. And such a huge object has the mass that corresponds to a black hole with a size between that of a nucleus, atomic nucleus, and that of an atom. So it's just remarkable that you can pack so much mass in such a tiny region. But then imagine putting such a black hole at the center of a star. In fact, Stephen Hawking himself imagined that before he came up with the result that these small black holes can evaporate. And he suggested that maybe there is one at the center of the sun. And the reason that he suggested that is because at the time, it was known that we are not detecting as many neutrinos, electron neutrinos that are produced by nuclear reactions in the core of the sun as we expect. And one possible idea that Stephen Hawking suggested is maybe the energy output of the sun is not produced just by nuclear reactions, but maybe there is a black hole at the center of the sun and it accretes matter, and that process releases energy that is supplying a significant fraction of the energy output of the sun. So we are supposed to get fewer neutrinos than we expect because not all the energy is produced by nuclear fusion. And of course, now we know that that is not a good explanation because we were able, in fact, the Nobel Prize was awarded to those who experimentally demonstrated that the electron neutrinos produced by nuclear fusion in the sun are converted to other types of neutrinos. And that conversion is a result of the neutrino having a mass. There are 3 flavors of neutrino, 3 mass eigenstates of neutrinos. So there is a whole physics associated with this, the oscillations between neutrino species through the sun, as they go through the sun on their path to Earth. And therefore, Hawking's idea is not needed. But nevertheless, there was a paper just this year discussing the impact of primordial black holes on the evolution of stars, even though just a small fraction of them would capture a primordial black hole. We might look for those rare stars that look unusual. And what I showed in my paper is that because the size of these black holes, the event horizon is so tiny, they are not accreting as much mass as you might expect. Because just think about a black hole as the ultimate prison. You can check into it, but you cannot check out of it. Even light cannot escape from it. If you get close to the event horizon relative to your friends far away, they would see time slowing down and they would see a frozen image of you as you get close to the horizon. In a way, that's a good thing because you're aging more slowly than they are. You might show them photos through Instagram that imply that you are still much younger than they are, as they are aging much faster than you are because of the deep gravitational potential well of the black hole. But once you cross the horizon, there is no way for them to get your direct messages or Instagram photos. And then you are doomed to go to the center of the black hole because what used to be the distance from the center turns into a time coordinate. And since time flows forward, you have no choice but to fall to the center. There is no way to escape that fate. And then eventually, even in the case of the biggest black hole in the Milky Way galaxy, which is at the center, it has 4 million times the mass of the sun. Even there, the size of the event horizon is roughly 1/10 of the Earth-Sun separation, and it takes less than a minute to cross that distance, falling towards the singularity. So even for that giant black hole at the center of galaxies, it doesn't take a long time before you reach the singularity. And once you get there, the tidal gravitational force is so big that it will rip your body apart. So even though on the outside of the event horizon, you might enjoy the benefit of aging more slowly than your friends, That's a blessing in disguise, because if you happen to cross the event horizon, it's a death machine. And you might ask, why are black holes so fascinating to so many people? Just because, for the same reason that many people enjoy watching horror movies.
Now, the image that the outsider sees of you falling into the event horizon of the black hole sort of makes black holes the Instagrams of the universe in a way. But beyond that, what happens to that image? Does it eventually just redden and fade? What goes on with that?
Yeah, so there is no information that can come out from the interior of the event horizon, and therefore the only thing that remains is the image from the time that the person who falls in just crossed the horizon. That's the only thing that you can see as the last image, and it gets frozen and redshifted and fading away, just like the last image in a classical Western movie. By the way, the same appearance characterizes what happens to galaxies in an accelerating universe like the one we live in. Eventually, all the galaxies far away will be separated from us, and they will cross our cosmic event horizon. And when they do that, we will only be able to see the last image from the time that they cross the horizon, and it will redshift and fade away in exactly the same way as in the case of a black hole. Now, a black hole is the ultimate prison, as I mentioned. You can get in. It's just like Vegas. Anything that happens in Vegas stays in Vegas. And the same is true about a black hole. Once you get inside, nothing can come out. But think about an atom. If the size of the atom is bigger than the size of the horizon, it's just like trying to imprison a plump prisoner. Imagine a prison that is smaller than the size of the body of the prisoner. You can't do that. You can't squeeze the prisoner. I mean, you can get a finger of the prisoner into the prison, but that's not enough. The prisoner could escape. And so when dealing with these primordial black holes that are smaller than the size of an atom, one has to ask, what happens to material falling into them? And what I showed in my paper is that they will potentially accrete material, but much more slowly than you expect. And, they can accrete one atom at a time. So, for example, at first they will absorb the proton, if it's a proton-electron gas, and then the black hole will get charged. And you can imagine a black hole atom that binds an electron to it by not just the gravitational force, but also the electric force. And it's sort of an extension of the hydrogen atom, except that now you have a nucleus that includes both an electric charge and a gravitational force, a mass that binds the electron. And so the energy levels of the electron in such a bound state would be different than the hydrogen atom. And I call that a black hole atom. And then eventually there would be a chance that the electron cloud, which is in quantum mechanics, particles are described by a wave function. And it's sort of like a cloud of the electron. It's not localized at any particular point. But there is a chance for this cloud to overlap with the event horizon of the black hole and eventually collapse there and end up inside the black hole. And I calculated that probability, and it's the resulting accretion of an atom is much slower than you expect if you were to assume some continuous fluid that falls into the black hole the way everyone else in the literature discussed. And, I submitted the paper for publication and wrote an essay about it in medium.com, and then got an email from a physicist, Paul Davies, who back in the early 1970s worked on quantum mechanics and gravity. And he told me that he attended a conference back then and suggested to examine this exact process that I was solving. He suggested it to John Wheeler, who was one of the pioneers of black holes. In fact, he coined the name. And John Wheeler said to him, I gave this problem to my student, Jacob Bekenstein. But at the time, Stephen Hawking derived his important result in response to what Bekenstein was working on. So Bekenstein got distracted. He never published anything on this question. And here I am 50 years later solving this problem that they talked about, but never really published a paper about. So I felt quite good about it because I thought about it completely independently. And, it's the kind of pleasure you get from the notion that great minds think alike.
The idea of the universe mimicking a black hole, to go back to that for a moment as it expands, does the universe in many ways sufficiently mimic things that happen with black holes enough to suspect, and some people have said this, it's been floated, that the universe may actually be a black hole or the result of one? What are your thoughts on that?
Well, the universe is expanding and it appears uniform in space to 1 part in 100,000 across large scales. And as we go back in time, in fact, the entire universe was uniform to that level. There were no objects, no galaxies, inside of which stars like the sun form, next to which debris made planets like the Earth, on the surface of which we exist. All of that did not exist in the early universe. There were no galaxies, no stars. In fact, it was a soup of elementary particles, and that is very uniform to 1 part in 100,000. And that's not what you get from a collapse to a black hole. Very often you get a highly non-uniform distribution of matter. In fact, the matter ends up at a point, what we call a singularity. We don't know exactly the nature of that singularity because we don't have a quantum theory of gravity. And in addition, the matter is not expanding once it collapses into a black hole. So it's really a very different situation that we're facing in our universe. And, there is a fundamental question of what created our universe. Why did the Big Bang happen? What happened before the Big Bang? And it remains an open question because we don't have a predictive theory of quantum gravity. We know that Einstein's theory breaks down when you go back to the Big Bang because the density of matter diverges and the curvature of space-time diverges. And we just don't know what happened at those circumstances. Quantum mechanics should remedy our ignorance because it would be able to deal with those conditions when quantum mechanics played an important role, and instead of the singularity, that singularity would be replaced by some sensible conditions that led to the Big Bang. If we had a theory of quantum gravity, we could have figured out what preceded the Big Bang. And I'm saying that because it's important. It's similar to knowing the recipe for making a cake. You know what ingredients you might need and how to process them in making the cake. And once you have that recipe, the next question is, can you create those in a laboratory? Can you bring those ingredients together and process them in the right way to create a baby universe in the case of quantum gravity? And if that's possible, then in principle, we could apply for the job of God. Or let me put it this way, whichever civilization developed an understanding of quantum gravity, they can, in principle, build a particle collider or some other laboratory setup that will bring them to the conditions necessary to create a baby universe. And they could apply for the job of God. Because the job description of God, the first requirement would be you should be able to create a universe. And if you can do that, you can do anything, because inside that universe, everything may happen if it resembles our own universe. And so the fundamental question that I would like to know the answer to is whether the Big Bang in our universe was created by a scientist in a white lab coat.
There's a lot of interesting ideas. You mentioned Paul Davies, and this actually was something that I believe he advanced at one point, was that maybe you could search the cosmic microwave background radiation for either iterations of a past universe or a SETI message left by that alien species that might have kicked off the Big Bang. Now, the quantum theory of gravity that is so elusive, do you see any avenues right now within physics that might lead to predicting quantum theory of gravity. Do you think that we have any leads at all, or is it still just entirely a question mark?
Well, the main challenge is that the relevant energy scale, which is called the Planck scale, is 19 orders of magnitude above the rest mass energy of a proton. Currently, our best collider, the Large Hadron Collider, is only reaching up to maybe 10,000 times or 100,000 times the rest mass energy of a proton. So we are very far away from getting close to the Planck scale. And the question is, where can we actually get some guidance as to how to construct a quantum theory of gravity? And one possibility is in singularities, but for that you have to enter a black hole. And I would not wish that on my friends. I mean, I have many colleagues who work on attempts to develop a theory of quantum gravity, string theories, and I would not like to advise them to go into a black hole, because they would never be able to write back about what they found. And in fact, they would not even have enough time to write the scientific paper as they get close to the singularity and test their theories there. Another possibility is going back to the Big Bang and detecting maybe gravitational waves from that period. And of course, there are attempts to do that, to detect the signatures of either cosmic inflation or whatever happened close to the Big Bang. In fact, if there was no cosmic inflation, I wrote a paper suggesting that we should detect a gravitational wave background, a background of gravitons, just like the cosmic microwave background, except it was produced at the Planck time, when the universe had the Planck temperature, and it should be a relic with roughly a temperature close to 1 degree Kelvin, above absolute zero, compared to the 2.73 degrees Kelvin that the cosmic microwave background has. And if we find this background of gravitons, it would tell us that inflation didn't take place, because in all models of inflation, it dilutes any primordial graviton background that was produced before inflation, because the universe goes through exponential expansion and everything that predated inflation gets diluted. So if we find the graviton background by some novel technique, first of all, we could study the imprint of quantum gravity from that early time, and also it would exclude a period of cosmic inflation. That would be very insightful. The only problem is, I wrote a paper about it, it's very challenging to detect the graviton background. I also wrote a recent paper just from a few weeks ago, I published it, that talks about the mass of a graviton. You know, we assume that gravitons have zero mass, that's according to Einstein's gravity, but in extended theories of gravity, those that deviate from Einstein's gravity, the graviton could have a mass, and I was able to derive a very tight limit, the best limit on upper limit on the graviton mass, that basically implies that its mass is practically zero and not important for anything that we study within our cosmic horizon. So this is another way to find about quantum gravity, going back in time to the Big Bang. But it's also very challenging, because detecting gravitons or gravitational waves is not easy, especially from those early times. And finally, you know, it may well be that some properties in the present-day universe were affected by quantum gravity. For example, in addition to dark matter, there is dark energy. And that is the energy density of the vacuum that is basically dominating right now the mass budget of the universe. Matter accounts for maybe at most a third of the mass budget right now, and 2/3 are the dark energy, which is producing a repulsive force that is pushing galaxies away from each other. And that another name for it is the cosmological constant that Einstein thought about 110 years ago. And so the question is, what is the origin of this dark energy, the energy density of the vacuum? So when you take a volume of space and clear out the matter, there would still be some mass per unit volume or energy per unit volume, and that's the vacuum's energy density. And that may very well tell us something about quantum gravity. It's just that we don't know. It's very difficult to understand what is the origin of that. And there are some theoretical ideas, but it may well be that once we figure it out, we would realize that it says something really fundamental about a theory of quantum gravity. But at the moment, we are sort of in the dark in the context of dark energy or dark matter for that matter.
So say, to speculate a little bit, back to primordial black holes, say we found one just floating in the outer solar system. You know, there's one out there. And that seems to me to give us a laboratory to maybe begin to probe some of this stuff. But could we even get close to it? Or would we be okay, you know, dovetailing with your paper? And what could we learn from a primordial black hole as opposed to a giant stellar mass or whatever, that type of black hole?
Yeah, so in fact, it would be a fantastic laboratory for testing quantum gravity if we had a primordial black hole in the solar system. And that's not a crazy idea, because if primordial black holes make dark matter and they have asteroid masses, there should be plenty of them passing through the solar system. And in fact, if those black holes happen to have the mass of Earth or a few times the mass of the Earth, one of them could account for what is currently discussed as Planet 9. And I wrote a paper about the fact that maybe the reason why we haven't spotted the so-called Planet 9, it was inferred to exist based on its gravitational effect on other bodies within the solar system, trans-Neptunian objects. And if it's a black hole, it's not easy to see it. And we showed in the paper that, in fact, one way to look for it is that every now and then there might be a small iceberg from the Oort cloud that might collide with it and produce a flare. And we could see those flares with the Rubin Observatory in Chile that will start operations next year. So that's an interesting possibility. And of course, you can think, if we have a primordial black hole in the solar system, you can think of using it, because if you dump trash into it, it can turn into pure energy. And I actually wrote another paper where I said that an advanced technological civilization could make a moon out of a primordial black hole, can bring it to its planet. And if, for example, you imagine a primordial black hole that has a mass of about 100,000 tons, such a black hole, according to Hawking, would evaporate in 1.5 years. But if you dump roughly 2 kilograms per second into this black hole, by the way, 2 kilograms per second is what you get by flushing the toilet. And so just imagine flushing the toilet all the time, or taking that energy, that mass that comes down, the water, and letting it accrete onto this tiny mini black hole. It would keep it alive forever, because you will basically compensate for the evaporation of the black hole. So the black hole radiates. Left on its own, it would evaporate in 1.5 years, but dumping 2 kilograms per second on it could keep it with a constant mass. And what you're actually doing is converting the mass that you dump into it into pure radiation. So you're getting 100% efficiency in converting rest mass to radiation. This is the ultimate engine, where you get the maximum you can ask for. All the rest mass converted to energy, to clean energy. And if you imagine doing that on a moon, a primordial black hole that is moving around the planet, I calculated that in a low Earth orbit, such an engine would supply as much energy as the sun does. And so you can have a planet that is not near a star and is being warmed by a moon that converts 100% of the rest mass dumped into it into clean energy, and you end up using it for all purposes on the surface of that planet. So that is the perfect engine. You can't imagine something better than that. And you can throw all your trash on this black hole moon. And of course, you can imagine another engine where you put matter and antimatter together and convert them to pure radiation. That is, of course, possible. The only issue is that the Large Hadron Collider, or CERN in general, was only able to produce micrograms of antimatter, positronium, for example, the anti-electron, and antiprotons, very little quantities, and they are extremely expensive. So you can't really convert kilograms of antimatter because they don't exist, and to make them requires a huge amount of money. Whereas if you have a small black hole, a mini black hole, that you feed 2 kilograms a second, you just get that engine out of the trash that you throw into it.
It does make a lot more sense. And again, the problem with the antimatter, as you mentioned, is that it is the most expensive substance on Earth.
Yeah.
Because we have to produce it. But we can make it. It's just that it's expensive, so it doesn't really look like it'll ever be.
By the way, it's really interesting why we exist, because if there was a perfect symmetry between matter and antimatter in the early universe, then all of the matter and the antimatter would have annihilated into radiation, and you would be left in a universe that is filled with radiation, with a cosmic microwave background, and that would be it. And the only reason that there is a surplus of matter over antimatter is some physical process that created an asymmetry between matter and antimatter in the early universe. We don't know what it is. It's still an open question in physics as to what was responsible for creating this asymmetry. It was an asymmetry of 1 part in a billion. So indeed, most of the matter and antimatter are annihilated, but there was a slight residual or surplus of matter over antimatter, and that's why we exist. I should also say that we should be grateful to dark matter, because if it didn't exist, we wouldn't exist. And the reason is different. Ordinary matter that we are made of couples to electromagnetism, to light. So the ordinary matter was coupled to the cosmic microwave background, the radiation, early on. And it turns out that the universe was uniform, but there were small fluctuations in density at the level of 1 part in 100,000. And they seeded the formation of galaxies like the Milky Way. But on the scale of galaxies, the radiation was able to diffuse. It smoothed out the non-uniformities in the ordinary matter. So because the ordinary matter was coupled to the radiation, it was extremely uniform on the scales of galaxies early on, 400,000 years after the Big Bang. But the dark matter was not coupled to the radiation. And so it kept memory of the initial fluctuations in the density on the scales of galaxies. And then it seeded the formation of galaxies, inside of which stars like the sun formed, next to which planets like the Earth were made out of the debris of those stars, on the surface of which, one of these planets, the Earth, we exist. Life as we know it formed. And without dark matter, all of that would not have happened, and there wouldn't be any galaxies in the universe.
Well, a whole bunch of things had to come together. That's something that I look askew at. That's like, how? Well, that's interesting. So, for example, as you mentioned, the minute temperature differences causing clumping. Had that not been present, it would have just been a lattice of hydrogen atoms, as far as I can think of, or as you say, matter and antimatter would have fully annihilated with each other, and there'd be nothing but radiation. But yet these certain tunings seem to come to play, and it's one of the things that bothers me. I think about that a lot.
Well, it should bother you only if you feel that we were destined to exist and that we play an important role in this cosmic play. But I think of it more as a circumstantial role. And the reason I'm saying that is because the sun formed only in the last third of cosmic history. And then humans came on Earth just a few million years ago. Okay, so that's 1 part in 10,000 of cosmic history. And then modern science and technology emerged only in the last century, which is 1 part in 100 million of cosmic history. And so we came, the way we are right now, arrived to the cosmic play only at the end of the play. We also know that we are not at the center of the universe. We are just sort of next to a random star in the Milky Way galaxy, which is just a random galaxy. Since we are not at the center of stage and we came late to the play, the play is not about us. And I think it's really important to maintain a sense of cosmic modesty. And of course, we should appreciate the fact that we exist, but we are not at the center and we are not even at the intellectual center of the universe. That's my take. I think the most sensible thing to assume is that there were things like us billions of years ago. And claiming that we are unique and special is arrogant. And, in February this year, I was invited by the Polish government to Torun, Poland, in celebration of 550 years to the birth of Nicolaus Copernicus. And I talked about the next Copernican revolution, which is our recognition that we are not alone. And that's part of my research right now. By leading the Galileo project, we're searching for technological equipment that might have been manufactured by other civilizations and sort of arrived at our backyard.
I actually look at it as an even deeper problem than that, because I agree with you, based on the Copernican principle, that we're just one of a population of civilizations that have exist or will exist or have existed in the history of the universe, and that we're just nothing special. We're just another member. There may not be one close enough to interact with, but maybe there is. What do we know? But at the same time, when people start making the argument that we are alone and going past that and saying, well, we're probably alone, which is that arrogance. But not only that, it's also somewhat intellectually difficult to process, because that turns us into extremely unlikely unicorns living on a unicorn planet where a biochemical process happens only once and only here and nowhere else in the universe. And I can't hammer that home enough that looks really, really strange and very implausible to me. What do you think about that angle?
Well, it's a boost to our ego to think that we are unique and special. And, when Enrico Fermi asked some 70 years ago, he asked, where is everybody? That's a question that lonely people often ask. And these are the arrogant lonely people, because they expect partners to come next to them as if they're so attractive. But if you think about it, to find a partner, you need to put some effort. You need to leave your home, go to dating sites. Enrico Fermi didn't build a telescope. He didn't search the sky. And when people say it's an extraordinary claim that we are not alone, I say it's the other way around. It's actually an ordinary claim. And the extraordinary claim is to claim that you are really unique and special, and that you are surprised that nobody is next to you. And, if you look at the search for dark matter that we discussed before, there were billions of dollars invested over decades, and we haven't found it. And if you ask how much money was spent in the search for cosmic partners, the answer is less than 1% of that. My point is that we should invest billions of, if not tens of billions of dollars in that, because this question is extremely interesting from the public perspective, and the public pays taxes, funds science, and we have an obligation to address a question that is of great interest. And moreover, it will have a huge impact on the future of humanity if we find a partner. Steven Weinberg, in his book, The First 3 Minutes, towards the end, he says, the more the universe appears comprehensible to us, the more pointless it seems. And from my perspective, it appeared pointless to Steven Weinberg and many of my colleagues, just because they imagine it being a mix of elementary particles, rather than imagining the possibility that there is intelligence out there. And, we already are at the cusp of creating artificial intelligence that will surpass us within the coming decade. So AI is an alien intelligence, because these computers are made of silicon chips. They're not made of flesh and blood. And when we try to train them to align with our objectives and the way we think, it might be just like putting lipstick on a pig, because we're talking about a very different intelligent entity there. I think AI should be thought in a broader term, because it could also mean alien intelligence and that we might find in the sky if we only search for it, if we allow for it to exist. And just to give you an example, a decade ago, there was a meteor that was moving extremely fast and was identified by the US Space Command and by US government satellites to have originated from outside the solar system. It was the first recognized interstellar meteor. Half a meter in size, collided with Earth and exploded in a fireball over the Pacific Ocean. And if you just do the simple statistics of such objects, assuming that, based on the rate of which we find them once per decade or so, you end up concluding that there should be 1 million such objects within the orbit of the Earth around the Sun at any given time. And only once per decade, one of them collides with Earth as Earth is moving around the Sun. Most of the time, they don't collide with Earth, but we cannot see them. We are blind to them because they don't reflect enough sunlight to be picked up by our best survey telescopes. So my fundamental question is, why not study those 1 million objects at any given time that are between the Earth and the Sun, that came from outside the solar system, and try to check if there is any space trash, any technological equipment like Voyager, New Horizons, Pioneer, that we launched out of the solar system, or the Tesla Roadster car that Elon Musk launched as a dummy payload on the Falcon Heavy in 2018. So among the rocks that arrive to us, among the icy material that comes from outside the solar system, there might be some space trash that accumulated over billions of years and was produced by extraterrestrial civilizations. And, with a few $1 billion, I can come up with a research plan that would do just that. If I was given $1 trillion, I could do much more. And $1 trillion sound like a lot of money, but in fact, it's what the US Department of Defense is using in 1 year, just for military purposes. And, if you think about it, it's money spent to protect the United States from threats or to attack other entities that may threaten the safety of US citizens. And so, in a way, if we just gave up on that task for 1 year, we could learn so much more about interstellar space and whether we have a neighbor. And I just think that we are misguided in our sense of priorities.
We will have plenty to say about the Department of Defense in the next segment of this interview, which will come out next week. Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.